All right, I think we're going to get started. I'd like to welcome everyone to the Early Career Lightning Talks for LDAV. And I'm really excited for this. This is a chance for our early career people to give us an idea of what they've been working on. So I'd like to hand over the floor to Niels. Thanks so much.
Yeah, hi, thank you. My name is Niels Dreyer. I'm from German Climate Computing Center. And I started there in May with the task to implement in situ processing for climate model. And in this lightning talk, I want to show you what we have achieved so far. So I want to start with a short introduction into our climate model. It is called ICON, and it divides the sphere, the surface of the globe into triangles. For example, for climate simulation that is like 100-kilometer resolution, which leads to 20,000 cells. And one special feature of the climate simulations is that they couple the ocean and the atmosphere. So we have two domains where we have different physics, but they are interacting with each other. And the usual workflow looks like that you run the model, write the output to disk, and when the simulation is finished, you start to process and analyze your data. Now, how does that look in the future? So currently the domain scientists are working on a setup that uses a 1.25 kilometer resolution for the horizontal grid. So that leads to 335 million cells. And if you use 100 layers vertically, you would need 125 gigabyte for every 3D field that you want to store, and for every time step. So if you want to store or handle multiple fields over a long time period, that would be a huge amount of data. And this setup currently runs on 900 nodes on our supercomputer, so that 900 nodes have 115,000 cores. And currently we have a throughput of 2 simulated days per day. Now, what are the challenges when we think about the workflow? So, in particular, the visualization and analysis workflow. So, one point is that we have one challenge is that we have a lot of cells. So if we think about a 4K display or 4K image, for example, that has 8 million pixels, and if you want to visualize 300 million cells on that you even don't have 1 pixel per cell, not even close to that. So you somehow have to downsample that or cropping to reduce the data in that point. Another challenge, or that is somehow related, is that you want to do it with in situ processing. So your processing scripts should be run with the model together, so that you don't need to store the output to disk, but you can forward it to the processing script, do your processing while the model runs, and then forget the data you have analyzed. Now, the solution for this is that we want to use a coupler for that. I already mentioned that the model is coupled. So we have one part of our nodes are simulating the atmosphere, and the other part are simulating the ocean. And in between, so the library that manages the communication between these components are the coupler, and we are using YAG there. And that organizes the communication between those two parts. And another feature that the coupler does is grid interpolation. So, for example, if you have data on an unstructured grid like that, the coupler interpolates that on any other grid that you have, for example, here a regular grid. So you are very flexible with the geometry or the grid that you want to use. And those two features are actually solving the challenges I mentioned in the slide before, because when we want to do in situ processing, we just can add a component more to our coupler, so that we have one additional component, and that can define its own grid. And this grid can also be coarser or smaller than the actual grid, and with that we can reduce the amount of data. And in the first approach, we used ParaView, a component that implements ParaView. I don't think that I need to explain what ParaView is. It's a de facto standard for scientific visualization. And here you see, for example, the clouds over North America with the topography. So you can see the Rocky Mountains, and the clouds and the color of the clouds decode the temperature. And now that, as I mentioned, we added an additional component to our YAG universe that we called Yavis. And that defines internally an arbitrary grid, whatever you want to have in ParaView then. And it obtains the data from YAG. So that we have this like from YAG to Yavis, and Yavis forwards it to ParaView, and ParaView generates the images online. So that we have in a prototype stage, and it's one approach we can use. The other approach we used so far is using Python. So we created Python bindings for YAG, and that makes it really easy to implement or prototype YAG components that you can attach to your model. And then you have the whole Python universe with all its libraries and packages available, like Matplotlib, Cartopy, and so on. So that's a very comfortable way and easy way to do in situ scripts with your model. Okay, I want to show you a short video that I made with these Python bindings, so that you can get an idea of what we can do there. So in the background you see a global grid with a resolution of 2000 by 1000, so that's downsampled and plotted then globally on a Mollweide projection. And that's actually a satellite image and the clouds on it. Then in the inset at the upper left, you see a zoom in on Barbados. So in Barbados, there is a cloud observatory. So the cloud structure there is like of special interest. And I used there 500 times 500 grids that I defined in my Python component and visualized it there. And on the upper right, you see the temperature track of 3 cities in Hamburg, New York, and Sao Paulo. So that tracks the temperature at these special points. So I use there just 3 cells at these points to evaluate the temperature at this point. Yeah. Okay. So to sum up, what we've done is that we think in situ processing as components for our coupler. And the coupler is like a unified interface for getting data from the model. And we have 2 like implementations of that. One uses ParaView or Catalyst libraries. That's for high quality 3D renderings. And on the other side, we have Python bindings for rapid prototyping and which is really easy to learn and have a lot of libraries available. Okay, with that, I'm done. Thank you. And especially thank my colleagues, Florian and Moritz, for their support and the nice start I had at DKZ. And at least I want to mention that we are looking for colleagues. So we have some open positions. And if you're interested, please visit our homepage. Thank you.
Thank you, everybody. While we have our next speaker setting up, we do have time for a question if anybody has one.
Hello, Charles from Kitware. Just a small question. Will the implementation be available in the future for other users?
Sorry, I don't get it.
Will the implementation of this be available as open source in the future?
Yeah, this is all open source, yes.
Yes, really cool. And just which version of Catalyst did you use?
Sorry.
Which version of Catalyst did you use? The first one or the second one?
I use the second version of Catalyst, so with the conduit interface,
Okay.
or with the conduit structure. Yeah,
that's really cool.
Okay.
Thank you so much. I'll introduce our next speakers, Kiyo, and he's going to be talking about instant neural representation for interactive volume rendering.
Okay. Hello. Hi, everyone. My name is Qi Hu from University of California, Davis, and I'm also with the Argonne National Lab. And today I'm going to talk about my recent work on instant neural representation for interactive volume rendering. And I want to show you guys how to instantaneously construct a neural representation that's produce almost identical visual images, and also at the same time render a terascale data on a single desktop interactively. So volumetric field is actually a mapping from a 3D coordinate to the n-dimensional vector. And in our case, we can just simplify n to be 1, so we look at scalar fields. Traditionally, volumetric fields are sampled discretely and represented using 3D grids. However, such a representation can be really huge and complicated when the resolution is becoming very high. And then the natural solution is to compress the data. However, compressing the data will reduce size, but the compressed data cannot be sampled directly. We have to decompress it in order to use it. So we really want the representation that's easily accessible while being still compact. And recently developed implicit neural representation give something like this. The idea is to use a neural network to approximate the mapping from spatial coordinate to data values. And the data is being learned by the network weights via regressions. The trained network weights can be then considered as the compression output. So it is very compact because we're just storing order of magnitude less numbers. And we can also directly access those values by inferencing the network. So all the requirements we ask for are fulfilled. So implicit neural network has been recently used in many fields, such as nerve or 3D modeling. And it can be built directly using fully connected networks or multi-level perception, NLP. To allow the network to capture high-frequency details, spatial coordinates are often being mapped to high-dimensional vector first, and we call it feature vectors. And this step is called position encoding. And one of the latest development of this position encoding method is the multi-resolution hash grid encoding. And we found that this method is particularly effective even for scientific data. So to train a neural network for volumetric data, we need 3 steps. First, we need to generate coordinates randomly within the domain. And then we sample the randomly generated coordinates using the ground truth data, ground truth volume. And finally, we use this coordinate and value pair to backward optimize the neural network. Repeat this step, we gradually get the result better and better. And we have 2 steps to make the process very, very fast, because that's what we want. First is we want to implement everything in low-level language, such as CUDA. This reduces overhead across the board. And then we want to use GPU acceleration if possible. In our case, we utilize the tiny CUDA library, which provides tensor core acceleration directly, and is about 20 times faster than a native PyTorch GPU implementation. And this allows us to create something like this, where we only need to spend 25 seconds to get almost indistinguishable images. And the metrics shown in the screen is the image difference. And we can keep training the network if we have the time budget available and get much better results. So to render the representation interactively, special rendering techniques are needed. And we developed 2 special techniques following different principles. For example, we can allow the neural network to be directly inferenced in the shader program. This requires a customized CUDA inference kernel, and it generally resembles the mega kernel paradigm for writing an interactive ray tracer. To enable hardware acceleration, some low-level synchronization are required, but it does not really fundamentally change the architecture or the structure of a rendering algorithm. So this method is suitable for generally any type of rendering algorithms, only with like small tweaks. And similarly, we can also write the renderer in the like wavefront style, which gives which I call it like sample streaming method. In this method, sample coordinates are explicitly streamed out from the kernel to the global memory, and then we have a separate kernel for inferencing the network in a batch. This allows us to exploit more parallelism and a higher throughput. But then, because we are fundamentally changing how the renderer behaves, the rendering algorithm can be fairly complicated and tricky to write. But it allows us to work with any type of neural network. So we are opening a new space for development. So next, we also have like additional layer of acceleration to accelerate rendering, and we call it macro cell. This is not a new technique. This has been exist for path tracing for years. And a macro cell is essentially a set of n-cube voxels. I mean, it doesn't have to be a cubic, but in this case, we call it cubic. And within each voxels, we store some data like the voxel min and max, and the max opacity of the containing voxels. And with this data structure, we can easily achieve things like empty space skipping and adaptive sampling for ray merging algorithm, and local majorance time bound for path tracing algorithm. And this type of optimization, although being very simple, we found that they are very, very suitable for rendering neural representations. This is because for neural representation, sample costs become very, very high. And this optimization exactly reduces the number of wasted samples we do in rendering. So it's very effective because this is optimizing the main bottleneck. And this is a result. We can see that the macro cell can give up to like 40x speed up compared to without macro cell acceleration. And we can also see that the sample streaming algorithm here is being faster. And why is that? This is really because the position encoding algorithm we use can be parallelized efficiently because different encoding level can be computed independently. So this is an embarrassing parallelizable algorithm. And because we are streaming the data out explicitly, we can use more GPU threads or GPU blocks to compute this step, and we get like about 10x performance speed up here. And now I'll give a so this is the this is the real-time capturing of me rendering like the 1 terabyte DNS datasets using my like single GPU workstation, and the frame rate is about 10 FPS. And this is rendering with volumetric path tracing with single direct lighting with next event estimation. And interestingly, we found that because our training implementation is pretty fast, which is about 1 millisecond per step, we can actually fit the training step inside the render loop and achieve online training. So we can repetitively refining the training while we are rendering. And let's look at a demo. So as you can see, it starts to look like data, even though we're starting from the scratch. We're starting from a randomly optimized the volume. And it's interactive, even though we are still doing training. We can enable denoising if we want, because we are doing path tracing, it's a little bit noisy. And if we think it's kind of slow, we can skip the rendering for a while and accelerate just by focusing on training. And then once we stop, the data looks much better. And we can repeat if we want. And it still remains interactive. So we believe this direction is still in this early stage, and there are many interesting topics that we haven't explored yet. For example, we can, instead of building like volumetric representation, we can look at surface representation, and there are already existing work, things such as deep SDF, might be suitable for this for scientific visualization. And we have also been looking into distributed data. In fact, we're actually presenting another poster in this week talking about this early preliminary result for this part. And we also want to explore multidimensional data structures such as AMR, unstructured volume, which are commonly used in modern simulations. Also, it's actually trivial to extend our work to multivariate volume, and there are already other existing work in this direction. And given our ability to do online training, we can actually start to change our mindset a little bit. And then we can, for example, construct other terms in the rendering equation using a representation. For example, we can learn the ambiguous occlusion term in real time, and when we get ambiguous occlusion. And furthermore, we are doing, technically we are doing volume compression. So for scientific analysis, it's important to improve accuracy, and there are still lots of room to improve in this area. And as earlier today, Professor Sen talked about in situ visualization, is actually a natural extension to for example, in situ net, where we can build the in situ surrogate model and outputting a neural representation, which is also very interesting. And this type of model should also be fairly useful just for regular in situ simulation, because now we can dumping lots of time steps using neural representation instead of raw data. And our representation is only several tens megabytes in size compared to terascale data or hundreds gigabytes of data. So also we can construct that fairly quickly, which makes it really, really nice. And this concludes my talk, and thank you for your attention.
Thank you so much. Do we have any questions? All right, well, for time, I think we're just going to keep going. Thank you so much, Chi. I really appreciate it. Our next speaker is Demi, and she is giving us a talk on machine learning for topological comparisons.
Hello, everyone. I'm Demi, and thanks for attending my talk. My topic is matrix learning for topological comparisons. So let's start with close to this. Let's start with some motivation examples and why we need to do topological comparisons. So the answer is, of course, data have shape, And we want to do like some of like a method to capture the shape of data, like especially for some complex large data sets. For example, here, like I put several like different data sets we can use like to do topological comparisons, like for ensemble data sets and 3D shapes and also scalar field. So the main idea is trying to capture the critical points by using the topological features. So actually topological like features, it can be seen as to understand the shape of data, and topological comparisons is to like compare the shape differences between data. And here's more like examples about data, complex data that has unique shapes, I will say. So here I put like some like cancer images and geodata and also graphs like power systems. So that means like topological data analysis actually is a tool to kind of like to abstract the shape of data, I will say. So which is combining like mathematical objects and algorithms to develop effective methodologies for data analysis through topological information. So since I've talked about tons of like topological informations, so what is like, here is like topological data analysis and machine learning kind of like combined together in order to do like two things actually. One is to able to do data analysis for large complex data set, which be used by using TDA to do a data abstraction. And second is we also want to utilize such kind of feature in machine learning pipeline. So that's why like recently like there's a lot of research about like how to combine topological data analysis and machine learning. So it's kind of like standard pipeline is giving input data, which is like some complex object. And then we will use a filtration function to create a sequence of increasing topological spaces so that we can get the topological features, and that can be encoded as topological descriptors based on persistent homology theory. And next step is to get a topological feature space, which is actually kind of like mapping the topological descriptors into a feature space, like vectors. Then you can use that kind of like representations as input to any type of your favorite machine learning task. And here's kind of like an example like to show like how can we capture topological features and giving images or a scalar field kind of function. So this image shows like a sublevel set filtration, and then how this like filtration, like I said before, is to create a sequence of increasing topological space to capture the change activity based on the critical points. So the main idea, like in a high level overview, is we want to not just a feature of space, like and we hope those type of topological features can also like incorporate geometry, also functions or maps of a space to capture like more sophisticated features. That's why we use like this increasing topological features to capture the change activity, I will say. And here's another example how we can capture topological features giving a data set that lives in a non-Euclidean space. So that's a Reeves filtration. And that's typically that can be applied with graph data set or point clouds. So since right now we are able to obtain the topological features, the next step is for matrix learning on TDA. That is actually doing one step further. Since we are able to get topological descriptor, it's already done kind of a data abstraction step to reduce the original data size into a smaller one in a topological space. And we want to do is to map the original like topological feature into a much smaller space, which I will call as representation space, while still maintain the similarity. the similarity I'm saying is the topological similarity. And that means we want to get, using matrix learning to get more concise representations that can maintain the quality of the original topological descriptors. So our work about learning similarity between topological descriptors is, here I've given example one type of topological descriptors, as I said before, it's about which is actually persistence diagrams. That is a diagram that encode the change activity with critical points. That's when it will appear and when it will be merged with other critical points. And the main idea is use machine learning methods to hash the persistence diagram into a binary code, so that the original, the distance between persistence diagrams can be transferred into a simple bitwise comparison between binary codes. And the main challenge is we want to use such binary codes do the distance comparison, but still maintain the original topological, maintain a similar similarity in the topological space. So since a time limitation, I don't have time to talk details about these methods, but feel free to ask me after this talk. Here I just show a result for medical images, for a large data set, which is 10K images, and then we are able to generate the corresponds topological descriptors. Here is persistence diagram for each image. So that means the size of diagrams is 10K, same as the image size. And here I want to highlight, so first of all, we get the topological descriptor, and then we're able to, so we can run the distance based on the original topological distance to get a distance matrix. And the next step is we can use our learned binary code that represent the original topological descriptors, and then we will run the Hamming distance to get another distance matrix, right? So in order to compare our learned representation, to compare the quality and the speed, we first evaluate the runtime for the original topological distance and the Hamming distance. So this result actually is a subset of this data set. So runtime for the original topological descriptors with its other approaches, the runtime takes the pairwise distance matrix runtime takes from hours to days. And our methods only take around less than 20 seconds. And actually, this one is only in Python implementation. We also provide a C++ implementation that will further speed up this distance comparison into milliseconds. And you can also see since the new representation is a binary representation, so the memory size will also be reduced. And we also use a Folk-Morrow score to evaluate the quality of distance. So since we get different distance matrix based on different representation, original one and binary one, and then we can run the distance-based clustering, right, from the two different distance matrix, and then we compare two clustering results using Folk-Morrow score. So here, Folk-Morrow score one means a perfect reproduction of the original topological distance, and our methods achieve 0.99. And here, so this one is for 10K diagrams, let's say 10K and 10K images. Our methods for the distance matrix only take minutes in Python. It can using the C++ implementation with hardware acceleration, it will take only seconds, not to say like less memory. Here is another result to show like how our representation can keep a distance of original like topological distance. So we plot like the topological distance as x-axis and Hamming distance from our binary representation as y-axis. And if most of points like flow into the diagonal, that means the distance similarity be preserved. So this result shows like most of the data points is close to a diagonal. So to summarize, my research is more like focuses on the topological feature space and machine learning in order by using matrix learning methods to design a better representation, better topological representations. And in order to achieve like fast and concise distance comparison for the original topological features, and to improve the overall performance of machine learning tasks by using that type of topological descriptors. So I want to say thank you for this NSF and DOE funding support my research, and thanks for my advisors, my mentor, my colleagues to introduce me in this community. Yeah. Thanks.
Again, we have time for one quick question if anyone has one. Yeah. Yes.
So thanks for your talk. I'm curious, you're getting a lot of compression. You're compressing things a lot. Do you have a sense of what type of information you're losing when you do that last step of getting the compressed space?
Yeah, my first intuition would be like, especially like when you do the distance maintain like hash things, in the original space, the smaller distance will lost. So suppose like in the original space, there's several, for example, giving one data points, there exists like several nearest neighbors for that. But when you like do compression, like map into a small space, there will exist like all of those like nearest neighbor will flow into one single block. That's the main, like the thing like we need to like think about like how to also not only preserve the similarity, but also preserve the rank kind of. Yeah.
Thank you.
Thank you.
Thank you, Demi. That was great. Our next speaker is Isaac Neely, and he's going to be talking to us about in-transit methods for immersive visualization.
One more time with feeling. All right. Hello, my name is Isaac. I'm a graduate student at UC San Diego, and I'm going to talk about some work that started as a summer internship with the Viz Lab at Argonne. So the use case here is some practitioner in the field wants to run a simulation that's too large to run in their local device, whether it's like a smartphone or a head-mounted display. They want to run that off in the cloud or in a supercomputer and stream the results back to their device, in the field. So I'm using some common tools. We've seen these talked about today, so I won't go over it in detail, but I'm using Sensei coupled with Catalyst, and our visualization client is programmed in the Unreal Engine. I'm using Kubernetes to handle all the orchestration and stuff like name resolution between my nodes, And a key piece of this is an open source library called Async, the asynchronous asset loader, which I'm using to actually load the meshes as they're streamed to the client. So a question I get a lot is like, why even use a game engine like Unreal Engine to look at scientific data? Isn't peer review good enough? And I've put some points here that came to mind, but I think the biggest one is the first one, which is that you can really quickly compile to all sorts of different devices. So I'm interested in AR/VR devices, but also just compiling to the same game, the same experience to Windows and Linux, is not necessarily an easy task. And it handles much of that for you. Some other obvious ones are if you want to put multiple people inside the scene, multiple users, that's already available to you through the multiplayer libraries. So here's the basic workflow for an in situ case where the simulation runs on some set of MPI workers. And then as each step completes, they are bridged to Catalyst, which executes a user-defined analysis script. So I'm using the extractor pipeline object available through ParaView. And a brand new feature just came out this summer is that you can define which ranks write their data. So you can, I'm just having every single rank write out what it does, but you might want to group by, same processes on a node, or sets of nodes that are computing, adjacent cells. You can do all of that through the configuration file. So the real simulation code I'm interested in is this coupled fire atmosphere model. I don't quite have that ready to present today, but I ran a proxy to show kind of what's going to happen. So the steps are that the simulation updates. Then you swap your cells with your neighbors, and then each one passes its current step to Catalyst, which executes the user-defined pipeline. So I'm running the Sensei oscillator mini app here, which is just computing the sum of some oscillators on a 3D grid, Cartesian regular grid. And it looks something like this, where each of the different colors represent a different rank, right? So it's showing that you're reassembling, the original object seamlessly. So does this thing scale? The answer is yes. I ran 2 different runs on 8 and 16 ranks with 8 processes per rank and 12 processes per rank to sort of compare if that communication overhead addition gives you some processing, some performance benefit. And it doesn't really, as you can see, it's scaling strongly with the number of nodes, not necessarily the number of processes. Another big takeaway here is that clearly the analysis step is the bulk of this this pipeline. It's about 15 times longer to actually do the filtering, pull out the isosurface, and do the extraction, write the file, than the actual simulation is taking. So that leads us to in transit. Clearly, you want to scale the data consumers, the workers that are executing the extraction step, quicker than you want to scale the simulation step. So you want to separate this into sets of kind of pure compute workers and analysis workers, and you want to scale the analysis workers more than the compute workers. So I don't have performance data for this yet, but the big takeaway is that to the end user at the edge, running the visualization client, it's totally identical, right? It's they're just talking to the workers that are generating the shape files. So how can you actually get from the edge to your cloud/supercomputing workers? So I've set up this system where I know I said write the file a few minutes ago, and all the in situ people were like, "Whoa, it's not in situ. You're writing a file." But I'm using a temporary memory-based file system. This is available through most Unix-like systems. I'm using the Kubernetes implementation. But this is similar to like a RAM disk. It looks like a disk, but it's the same speed as just like a copy. So each node, which could have any number of ranks, runs a WebSocket server. I've written it in Python. It's not the bottleneck, but maybe you'd want to make that faster at some point. So then you talk through a reverse proxy from outside the cluster, and that proxy is going to handle the routing to the proper node. So I'm just using URL strings to achieve this, right? So the worker would say like, give me node 0, and you just pass that through the URL. Proxy finds the correct node to give you, and you upgrade the connection and start talking. And then from there, you can do things like ask, what's the most recent time step? How many time steps do you have? Give me this time step. Those sort of communication routines. Another nice thing about this is that you don't annoy campus IT when you're trying to run your code, because this just all happens over port 80. It's TLS, so all the data is encrypted, and it just looks like normal web traffic as it comes across your campus border gateway, and then the proxy handles passing it to the correct worker. So then how do you play this back in Unreal Engine once you've pulled some time steps from the cluster? I'm using this fairly recent addition called procedural mesh. So this is a way that Unreal has let developers define things at runtime. This is usually used for like foliage or landscapes, things that don't have like a set mesh at compile time, and that might change when based on like the user input or the camera location, things like that. And this is where that library assimp I was talking about comes into play. It supports PLY, which is what the Catalyst is writing, but it also supports, you could do this with all kinds of shapefile formats. So you can, the naive method would just be sort of pull everything that you got, all the time steps you got, just stick them all into memory and toggle them on and off in the scene. That's gonna eat up all of your memory, but it does work, and that would be really fast. So that'd be sort of like if you need like a slider and you need to be able to slide back and forth through the time steps. What I'm doing for this demo here is just using a background process to pull the time steps from disk to memory. And then once they're paged in, I push it all together, so you don't see like a jitter between the different pieces of the mesh. The coloring here, I've defined one material just to highlight that this is coming from different ranks, which is the red in the lower corner, and the rest of them are colored by the velocity field from this simulation. So it's sort of the standard blue to red, cool to warm thing. And that's defined in the Catalyst script, but it does not have to be. You could change the materials that you're rendering with, at the very edge, right before you render, if you wanted to do something different. So you have that flexibility there. So it looks something like this, and the sort of jagged edge, I guess, is how it's just the edge between the different consumer ranks that are streaming this in. So if I wasn't doing that coloring if I didn't add that special red material, it would just look seamless, like the rest of it looks seamless. And you can see that as I move the camera around and stuff, all of the paging is happening in the background, and it's not killing your frames. So just some things that came up as I was figuring this stuff out. A really nice feature is that you can expose all of your C++ code to the editor, And you can then do, use nice visual scripting to do quick things. For example, that animation I just showed, took only about 10 minutes to program. Another thing that I'm currently working on is doing iterative decimation. And this way, if you're like really, really at the edge with like a horrible connection, you could still start receiving time steps, right away, even, and then as the connection improves or as time goes on, you could pull in the higher res steps. And I'm at my time, so I'm just going to skip this one, but thank you guys so much. It's been a real pleasure. Bye.
Yeah, I was just wondering if you were using FireTech for your wildfire atmosphere model.
I'm sorry, I didn't catch the name. Fire what?
FireTech?
FireTech. I'm not familiar.
Okay.
I'm interested. It's the FDS, the Fire Dynamics Simulator.
Thank you again. And then Cooper is our next speaker. He's going to be talking to us about a large image viewer.
Thanks. Hi, yeah, I'm Cooper Myra. I'm a second-year PhD student at Tulane, and this is my first time at Viz, so I want to take the opportunity to introduce myself to the community and talk about my research. Thanks. Yeah, so this is my second year. The vast majority of my first year, we've been working in conjunction with the Bird Foundation on this project that has involved mapping the seafloor off the coast of Israel. So the Bird Foundation has sponsored a lot of surveying with these unmanned submersibles that basically just take footage of the floor. It's kind of like satellite data, and it comes back as images that need to be kind of looked at and deciphered by people. The primary focus of this is to identify areas of instability where landslides might occur, because this has a big impact on drilling. Obviously, areas of instability and landslides will affect oil production, and once oil pipelines are on the seafloor and pumping gas, a landslide could be catastrophic as far as a leak. So because that's their interest, that is, of course, our interest as well. And our part of that has been working towards automatic feature detection. So this is what the data looks like. On the right here, the SAS imagery, that's the sort of satellite-like data from the submersibles. And this data also comes with a video feed that you can see there on the left. This is just kind of like a mounted camera perspective of what the submarine is actually seeing as it's moving along. So we know that there are these features in this data. We want to be able to get at them. We want to be able to annotate them so that we can hopefully train a model and get a labeled data set that can do that. So we partnered with some people in our geophysics department to annotate this data, basically like subject matter experts. But as they were using the existing tools, namely QGIS, ArcGIS, they were finding that navigating around these really large data sets of images was really, really cumbersome. It was really slow. It was really laggy. I think going through and annotating a data set is already like a really tedious task, and doing it with bad tools, it's like the worst. So we spent the vast majority of the last 2 semesters creating a new tool that would allow them basically just to navigate through this image data in a natural, easy way and annotate it. So the first thing that it needed to do was basically just navigate, right? We need to be able to zoom in, do this without lag, pan around. And because this is a large data set, this was somewhat difficult to do, but obviously the tool does that just fine. And the next thing that obviously was necessary was annotation. So users need to be able to start an annotation, click points around on the data to create a visual area that represents a feature of interest. And then once they've done that, they can mark that feature with a label. Okay, so this was basically everything that we needed in order for our subject matter experts to be able to annotate this data and create for us a labeled training set. But in addition to the SAS imagery, that survey data, as I was saying, there's also these video feeds. And so both the people at the Bird Foundation who were representing a perspective of industry and the people that we were working with to label this data, they wanted this video feed incorporated. And so that's basically where our viewer tool is right now. So we have video feeds. This particular survey session had 2 mounted cameras, so we have 2 video perspectives that represent the same moments in time. And these are geotagged, so in addition to the videos playing, we have their position overlaid on our image data there. And as the video plays, you can see the 2 videos are in sync, and the position of the current location moves in accordance with that. So basically the current location works as like a play bar, and as you fast forward around the video, it stays with that. So this is a tool that we're pretty excited about. I think it was fun to build, and we're hoping that it can become a lot more. As I was saying, we're working towards automatic feature detection, and so we're hoping to integrate that in a real-time sort of capacity so that it can be deployed to be used on boats, to be used during these survey trips. And so part of that has been working towards our automatic feature detection. So once we have these annotations made and we have these areas where we know features exist, we extracted them, and we did that by just creating 32 pixel by 32 pixel little squares so that the features are represented in a normalized kind of way. And then instead of just breaking these into a vector with the grayscale values, we're actually using Demi's research on topological data analysis to extract essentially like a clustering model. So this is basically the persistence diagrams and the similarities between them, and using that to train a machine learning model. So it's been a great opportunity basically to use research that Demi has done, and it's been giving us really promising results. And so that's been great so far. I would say our results are still fairly preliminary, but yeah, they're definitely encouraging. So the way that we were able to navigate around this image quickly was by using a pyramid model. Basically, we break this large image into a pyramid. This is not a new technique. QGIS actually has an option to do this, but we found that even when it was doing it, the experience was not seamless. It was still very slow and laggy, and it was really a frustrating experience. But this is important because as we try to improve our tool and make new ground with it, knowing that our cache only has to deal with a small subset of the tiles is very important. So part of that is working towards predictive caching. So this is something that's kind of new. We've really only started doing this in Python in like a very offline sort of capacity, but basically Maniotis and Thomas have this really great paper about a viewport-aware deep reinforcement learning model, and that's what we're trying to implement. So as I was mentioning, we're trying to see this tool deployed in the field sort of way. So that would be like our people on the boats with their computers in a really computationally restricted environment. So if that's the case, we need to be careful about how we manage our cache. We need to be careful about what tiles we're using and what memory we're consuming to do that. And so we're attempting to implement this technique basically where we use our cache very responsibly. We don't want to fetch too many tiles, and we don't want to fetch the wrong tiles. And so we're using a reinforcement learning model to, based on the user's own navigation and how often tiles find themselves in the viewport, pull tiles appropriately into the cache. So that's all. Thanks for your time. I'd just like to thank our sponsors at the Bird Foundation and the Department of Energy. Appreciate it, and I appreciate having the opportunity to introduce myself. Thanks.
Thanks, Cooper. That was really nice. If we don't have any questions, I'm just going to keep moving on for the sake of time. Our next speaker is Dylan Cashman, and I'm sorry, Dylan, I don't have the title of your talk.
Hi, everybody. Sorry, I think they're going to turn up my mic. Okay, great. All right, well, thank you everybody. As I get my slides up here, I'm gonna try to go pretty quick here because I know it's the end of the day. Thank you for staying till the end. Okay. Are you seeing the, okay, no problem. Is this working? Okay, awesome. Let me get a timer out too. Okay. All right. So anyway, hi everybody. My name is Dylan Cashman, and I work at Novartis Pharmaceuticals. I got my PhD in 2020, and I've been working ever since. And today I'm going to talk about my experience there as a visual analytics expert. And I'll start with a little background on what my role is there. And then I'm going to go very quickly over 2 research projects I've led in the last couple of years. And hopefully, unless it goes super long, I'll talk a little bit about lessons learned, because I know I'm still friends with a lot of PhD students. I'm friends with a lot of other early career researchers who are very curious about what the differences are between an academic experience and an industry experience. And so hopefully my story will be interesting to you guys. So first, where do I work at Novartis? So I'm in the data and AI division, and my group is called Insight, Strategy, and Design. And we work more on the operational side. So we develop analytics applications like the kind you see in the screenshots there. We call them control towers, and basically they have visualizations of data. There's typically like a machine learning backend that's generating predictions. And the goal is to mine all of our operational data to generate insights that can then stimulate actions by the company itself, change strategy, that sort of thing. And my group is a lot of domain scientists and machine learning engineers, and they brought me in because they realized one of the most important questions they had to answer in designing these applications is, what do users want from big data? And importantly, is that actually what we're delivering when we sort of go through our analysis of that big data? So I'll define big data in pharma. It's a different scale than maybe the last few talks, but for me, it's still pretty big data. So in pharma, there's a wealth of patient data, obviously. So every interaction with the healthcare system is interesting to pharma. But there's also a lot of operational data. One of the reasons why is it's a highly regulated industry. So you have audit trails of every single thing that the company does. And there's probably a lot of value in that data, right? So just as an example, clinical trials are kind of the bread and butter of a pharma organization. And at any given time, we would have thousands of trials ongoing with tens of thousands of sites those trials are held at, hundreds of thousands of participants in the trials, millions of visits with clinicians. Each visit would have, lab data, unstructured text, lots of data, right? And we also would analyze tens of millions of healthcare claims and patients, manufacturing data even, because we manufacture our own drugs, financial information, and even social media listening. So really there's a wealth of very heterogeneous data that we would consider operational that maybe we want to learn from. And the problem that we encountered is we had really good analysts. They'd come up with really good predictive models, but the way that they presented them to the subject matter experts that were making decisions would sometimes feel like a lost in translation moment, right? And so it's kind of a frustrating problem because you have everything you need, you think, but something's not really forming, right? So I'm going to talk about 2 projects that tried to address that in the last couple of years. So the first is trying to help out data scientists in maybe how they present their results. So as a viz person in a group without a lot of viz people, I would encounter this situation, maybe you guys have been there too, where someone would have some slides and they'd come to me and they'd say, okay, you're an expert. Like, what do you recommend? How do I change this to make these slides better? And I'm going to explain one example where a data scientist came to me and he had developed a model that made some prediction on studies. And he developed a newer version of the model. And he was really happy because the newer version had lower error than the old version, right? And he had presented it, and these are the visualizations he had used in his slides. So on the left side, you can see an ROC curve. And on the right side, it's sort of a table where the left column is the old model, the right column is the new model. And then he has, just the textual representation of the amount of the percent of error that he'd have on an average study. And he was kind of upset because the subject matter experts saw this slide and they didn't really know what to do with it. And you can sort of see the point here, right? Like an ROC curve is very meaningful to a machine learning scientist, not very meaningful to the consumer of the model, right? So I came back to him and I said, okay, I think let's get rid of the ROC curve and maybe I have a better visual encoding for you for representing error that you're calculating. And he liked it, the subject matter experts liked it, but I was trying to explain to him why I thought this was a better representation than what he had had. And it sort of led me into an interesting research question. And basically, we have lots of visualization rules that say, what chart should you use if you have a visual encoding and it's categorical and numerical data. And we have these rules of thumb that say, don't use a line chart with categorical data, for example. But I was looking at this is a visualization of a computed value, and there are really rules of thumb that we have for computed values also, and I would argue that they're not really as well written down, right? So what I did for this is I looked at the calculation of error that the data scientist was using, and they have all these calculated values that they want to communicate. So for the error calculation on the top right, you can see it's a sum of n elements on the numerator divided by n. And there's all these qualities about the computation that might imply certain rules of thumb, right? So if it's an average, which we can imply from the computation, maybe that means we show distribution, right? If it's an aggregation of instances, maybe our visualization should include individual instances or outliers as well as the average. If it's comparison, because we have a function of y on the top of the fraction and a function of y on the bottom, maybe we use that sort of part of whole visualization from the previous slide. So this is very early stages for me, but basically I was thinking about how can I help the data scientists generate these types of visualizations automatically. And I think what we can do is build a grammar around the functions that are being run on the big data. And so once they finish their analysis, that grammar can just automatically generate visualizations that are a better fit for what the subject matter experts actually want to see in the computation. But as I started that project, we sort of decided we wanted to step back a little bit and understand better what the subject matter experts actually want. So this is an interview study, and it was primarily conducted by two interns, Ashley Sue and Gabriel Appleby. They're PhD students at Tufts University. And it tried to get at this question and maybe take an assumption that maybe the two sides don't actually want the same thing. Maybe one of the reasons why we have a lost in translation moment here is, the data scientist wants lower area under the curve, and the subject matter expert wants to make sure that there's very few outliers, right? And our hypothesis was that maybe we can get rid of this translation problem and get the two sides to talk to each other better if we use visualization as a medium between the two of them. So we ran an interview study where we did iterative interviews with both data scientists and subject matter experts at the same organization. And we thought that that was a unique opportunity, right? And we asked about examples of collaborations in their careers that did work and didn't work. This work is actually in submission right now, so hopefully you'll all be able to read it in your favorite publications. But from our findings, we developed a list of prescriptive guidelines that data scientists can use to make their presentations better. And we also developed notebooks that would automatically generate visualizations given just a model and its predictions. And so from these two projects, I think the big takeaway that I've had in my career so far is that the impact of big data, the impact that you want to get out of it, is really a function of three factors. So the quality of the data is important, the analysis you do is really important, but the presentation of the analysis is maybe where Viz comes in for me. And I think that these three factors are multiplicative and not summative. And that means if one of them is zero, the impact is going to be zero. Now, my experience is in industry, they invest a lot in the quality of the data and the analysis. And I think they underinvest in the presentation of the analysis. So I think that's good news for us. I think that the presentation is sort of the limiting factor, and that means there'll be a lot of demand for visualization background. But I also think, and this is where my two projects have led me, that extending our automated presentation tools so that the floor of presentation of the analysis is raised is one way that we can have like a really big impact on how people use big data. Okay, so very quickly, I have a very short list here of some of the lessons that I've learned. So sort of the positives and the negatives of working in industry compared to my PhD. So obviously data is like a really good reason to go into industry. There's a lot of interesting data that's proprietary that you don't get access to. You can learn a lot about a domain. You know, I get to talk to scientists every day. And you have a lot of access to users too. The two in the middle I wanted to point out, because I think these weren't as expected to me. So as a visualization expert, sometimes you have to sort of carve out your role, right? So I was hired at the same time as machine learning engineers, and people kind of know what a machine learning engineer does. Sometimes you have to advocate, right? Or else you'll get pushed towards other things. So I was sort of pushed towards being a data scientist, and I had to keep saying, no, trust me, there's a lot of value in the visualization. And then the data access, even though there's a lot of interesting data, it's a different situation, right? Because the data has proprietary value for the organization you work for. Sometimes it can be kind of touchy, especially getting to publish on it, which can be frustrating. But the last point I want to make is that they really need us and they really want us, right? So the users love talking to me because as visualization people, we're trained in user-centered design, we're trained in doing interviews. And I think that gets missed a lot in application building. So that's the end of my talk. Thank you so much, and I hope everybody has a great day. Yeah.
Does anyone have any questions? Okay, I think I'm just gonna wrap it up since
please.
we're sort of at time, but I will invite everyone to come talk to our new early career folks, or old early career folks, or very old early career folks at our early career meetup on Tuesday p.m. at 5 o'clock. I'd also like to invite everyone to come talk to anybody that are national labs on Thursday, I think around the noon time. For another meetup. And so any of that information you can find on the website for the meetups. But let's give our early career people another round of applause. And so my last responsibility is announcing the LDAV best paper. And so this year we have chosen the paper titled Distributed Hierarchical Contour Trees by Hamish Carr, Oliver Rubel, and Gunther Weber. So congratulations on that. And finally, I would really like to thank the LDAV steering committee, the organizing committee, everyone who helped review papers, everyone that is here today. It's great to be back. It's great to see everybody. So hopefully we'll see you next year. Thanks again for attending.